Hello and welcome to our last presentation on Introduction to Turbulence. And what we're talking about now is how an airplane responds to turbulence. We'll start out first by talking about the basic physics, just very general Newtonian physics, and after that we'll get into aircraft design. So of course, Newton's laws of motion, his first law of motion, a body at motion remains at motion, a body at rest remains at rest, is the first law of inertia. Isaac Newton came up with this back in the 17th century. In other words, this is the equation at the bottom you see there, relates to momentum. And momentum is a function of the mass of an object and its velocity. Newton's second law says that the time rate of change of momentum of a body is equal to the force that's applied on that body. So in other words, how the momentum changes with time, or if you like, it's simply a function of the mass times the acceleration. In other words, the acceleration of a body is a function of the force that's applied and inversely proportional to the mass of the object. So basically what this says is that objects that have mass and also velocity have momentum. Objects that have a lot of mass and great velocity have big momentum. Objects that have little mass and little velocity don't have much momentum. So that brings us to aircraft design. And we're going to go through basic aerodynamics. Don't expect everybody in this class to have had aerodynamics already, so we're going to go over some basic aviation terminology. And the first thing we're going to look at is the airfoil, and the way we describe parts of the airfoil. The front end is the leading edge, the back end of the wing is the trailing edge, and the imaginary line connecting the front of the wing to the back of the wing from the leading edge to the trailing edge is the chord line. And as an aircraft goes through the air, it sees a wind that's blowing over the wing, and we call that the relative wind. It's the wind that results from the motion of the air, the wing through the air. So the angle between the relative wind as it approaches the wing and the chord line is known as the angle of attack. We also call that alpha. So that brings us to the lift equation. We need to talk a little bit about lift because lift changes with turbulence, and lift is a force, and the lift force is a function of the velocity of the aircraft through the air. It's also a function of the density of the air, and also something known as the coefficient of lift, which is a function of the angle of attack. And speaking of angle of attack, here's a plot of the coefficient of lift versus angle of attack. And you can see as the angle of attack increases, as the angle between the wing, the chord line of the wing, and the relative wind increases, so does the coefficient of lift. So in other words, this means that lift will increase as you increase that angle, as the airplane pitches up and gets a bigger angle between the relative wind, or the motion of the aircraft, and its wing. That happens all the way up to a certain point. You can have a maximum in the coefficient of lift at a point called the critical angle of attack. And at this point, beyond that point, the wing stops generating, or not stops generating lift, but it stops producing it efficiently. And you get turbulence, significant turbulence, which reduces the lift of the wing significantly. That point we call stall. At that point, the wing no longer wants to generate lift, or generates very less lift, and we say the wing has stalled. So here's a diagram that shows the chord line of the wing and also the relative wind. So that angle you see there is the angle of attack. And you can see as the angle of attack increases, the turbulence over the wing increases, and the lift increases up to the point where it no longer produces lift efficiently. You get lots of turbulence, and we have stall. One other thing we need to talk about before we get into turbulence and how turbulence affects the aircraft is the load factor. And what load factor is, simply, it's the ratio of the total air load acting on an aircraft to the gross weight of the aircraft. So in other words, in straight and level flight, when the airplane is flying along, lift is equal to weight. And if you put that into the equation, the amount of lift and counteracted by weight, you'd have a load factor of 1. But we measure the load factor in G's, so when I said 1, I should have really said 1G. At that point, lift is equal to weight in straight and level flight. But if the aircraft is accelerated and the wing has to support or generate more lift, then the lift will be greater than the weight, and you have higher load factors. An example is a load factor could be 2Gs, 2 times. The lift is generating 2 times the weight of the aircraft. So that brings us to our last point, which is the flight or limit load factor and the design or limit load factor. So we talked about exactly what load factors are. That's the amount of lift divided by the weight of the aircraft. But the flight or limit load factor is used in designing aircraft, and it's the highest load factor that can be expected in normal operations. So in other words, you look at the purpose of the aircraft and try and figure out all the maneuvering that it's going to do and how much maneuvering or how many G's or load factor will be generated by that maneuvering. Of course, fighter aircraft have very high limit load factors. I think that fighter aircraft typically have somewhere around 7 or 8 for a limit load factor, whereas smaller aircraft have much lower load factors, or G's, can withstand less G's. So, we design aircraft, or aircraft are designed to withstand these load factors without any structural damage. And here's some examples of other aircraft. Normal aircraft, 3.8 to minus 5.2. You can have negative load factors also in inverted flight or in maneuvering flight. But aerobatic aircraft, as you can see, have a much broader range of load factors that they can withstand. Whereas smaller aircraft or aircraft just flying along straight and level, not straight and level, but a general aircraft can experience or can withstand less load factor or less G's. The design or ultimate load factor is the load factor. It's the limit load factor multiplied by 1.5. In other words, you don't want to design an airplane so that it breaks as soon as it reaches its limit load factor. That would really make people unhappy, especially when they're falling through the air. So what you want to do is have kind of a buffer. You have this area that the airplane won't come unglued. It may experience some damage, but it'll keep flying, and we call that the design or ultimate load factor. It protects the airplane against unexpected conditions. You may exceed the limit load factor accidentally. So here are the factors that affect the load factor when you're in turbulence, and we'll talk about gusts and airspeed and also wing loading. So of course, as an airplane flies through the air, it's going to experience gusts, and we're concerned about vertical gusts. There's also horizontal gusts, but we'll talk about vertical gusts. And we talked about angle of attack, and how angle of attack is the angle between the relative wind and the quarter line of the aircraft. Now, when you experience vertical gusts, that will change your relative wind, and also will change the angle of attack. In smooth air, it looks like that. In gusty air, gusty conditions, you'll have a vertical gust, and if you add the vertical gust and the relative wind together, you'll get a new relative wind at a different angle approaching the airfoil. So that new relative wind with relation to the chord line produces a greater angle of attack. So as you fly through turbulence, your angle of attack is changing. And the change in the angle of attack depends upon the strength of the gust, how big it is, in other words, how fast that vertical gust is, as well as the speed of the airplane. As the airplane moves faster and faster through the air, those gusts become smaller components. But if the airplane is going very slowly through the air, it's a major component. So as your gusts occur, you have a new relative wind, which means the angle of attack is changing. So if you look at the angle of attack curve, or the coefficient of lift curve with angle of attack, you see that as your angle of attack changes, so does your coefficient of lift. Your coefficient of lift will change. And from your lift equation, that means that you have additional lift. You have greater lift. So if you have greater lift, that means that you have a much greater load factor. So as you're flying through turbulence, through these vertical gusts, your load factor is changing constantly, and you have greater load factor. So the load factor may be so great that depending upon the strength of the gusts and the weight of the aircraft and other factors, it may exceed your limit load factor. In other words, you can be outside of the envelope. If you're flying slow enough, the airplane won't exceed the design load factor. Instead, it will stall. And we talked about that already, how you can exceed the critical angle of attack just by increasing the, or changing the relative wind. Another factor that will affect turbulence, or how an airplane handles turbulence, is the airspeed of the aircraft itself. So as the aircraft flies through the air, the faster it goes, the more lift it generates, and as a result, it determines how much more lift is going to be generated by the gust when it experiences a gust. So actually, flying slower is better. You'll have the slower you fly, the smaller the change in the load factor. As a matter of fact, there is an airspeed that aircraft manufacturers recommend for aircraft called maneuvering speed. And below maneuvering speed, the aircraft will not exceed its limit load factor. Instead, it will stall before it reaches its limit load factor. However, above that airspeed, if you maneuver the aircraft and add G's to the airplane, in other words, you have a higher load factor, it can generate forces where it will exceed the structural limitations of the aircraft. In other words, its limit load factor. Finally, the other factor that takes care of or affects how an airplane feels turbulence is wing loading. So wing loading is simply the weight of the aircraft divided by the wing surface area. In other words, each square foot of wing is supporting a certain amount of weight or pounds of aircraft. So suffice to say, or you can take it on faith, that the change in load factor is inversely proportional to the wing loading of the aircraft. Which means that for higher wing loadings, the change in load factor is smaller. For lower wing loadings, the change in load factor is higher. Here's some representative wing loadings for various aircraft. You can see the Cessna 172, a lighter aircraft, has a very low wing loading, whereas Boeing 747 has an extremely high wing loading, which means that the Boeing 747 will not see a big change in load factor, whereas the Cessna 172 will. And also, larger aircraft tend to, with high wing loading, tend to ride through the turbulence and not get tossed about as much, whereas smaller aircraft will feel those accelerations more. Also, you can have gusts in the horizontal. We've been talking mostly about vertical, but a horizontal gust will change your angle of attack on the vertical stabilizer, and that will result in yawing motions. In larger airplanes, they have yaw dampers which suppress that.
The way that we describe turbulence in our atmosphere depends upon our measurement systems. One way of measuring turbulence is through a gust. We describe it as a gust, and that is measured by a differential pressure system. That measures static pressure, or pressure in one direction versus pressure in another direction. Another way that we can measure that is through an accelerometer in the aircraft, which is measured in Gs. Yet another method is actually calculation called the turbulent kinetic energy. Basically, it's the energy that the air has in 3 dimensions. But the method that we measure and describe turbulence in the atmosphere today is called the eddy dissipation rate, or EDR. EDR is a measure of the turbulent state of our atmosphere. It is how the energy dissipates in our atmosphere, and it is the ICAO standard as of 2001. Also, it is aircraft independent. It's like temperature, where you stick a thermometer in the atmosphere and you get a measure of how fast the molecules are moving. And as a result, some people feel it warmer, some people feel it colder, depending upon your senses. Same way with aircraft. The atmosphere has a certain amount of energy. Some airplanes handle it better than other airplanes. So that's what we mean by aircraft independent. Eddy dissipation rate, EDR, is not dependent on the type of aircraft. EDR is calculated using numerical models, and from that, and also the algorithms that we have to determine EDR, it is forecasted and plotted on graphics, which we call the graphical turbulence guidance, which is provided at the Aviation Weather Center. That was a quick overview of how an aircraft responds to turbulence and how we measure turbulence in our atmosphere. I hope you enjoyed this video. There are more videos on turbulence on my YouTube channel.